Welcome everyone to the California Science Seminar sponsored by the Fire Research Group. This is our last meeting of the semester, so we're very glad you can join us. This seminar series is organized by Michael Gollner from UC Berkeley, Crystal Colden from UC Merced, and myself, Janet Cobianiguez, also from UC Merced. Today, we're pleased to be welcoming our speaker, Professor Charles Ichoku from Howard University. And before we begin and before I introduce our speaker for today, I do have some quick announcements to make. So first of all, the seminar will take place during the first hour of our session. During this hour, participants are able to ask questions through the Q&A box of Zoom. Questions will be answered in the order that they are received. Following the talk, we will be hosting an extended hour of discussion. Everyone is invited to attend. Students and early career folks are very encouraged to join us there. It's a good space for discussion. A link to the discussion session, which is a separate Zoom meeting, will be provided on the chat box. So with those quick announcements and without further delay, allow me to introduce our speaker for today. Dr. Charles Ichoku is a professor of Earth and Atmospheric Sciences in the Department of Interdisciplinary Studies within the College of Arts and Sciences at Howard University. He is also a distinguished scientist of the NOAA Cooperative Science Center in Atmospheric Science and Meteorology. Dr. Ichoku received his PhD in Earth Sciences from the Pierre and Marie Curie University in Paris, and his MS and BS degrees in remote sensing and surveying from the University of Nigeria. And prior to joining Howard in the fall of 2018, he was a research physical scientist at NASA Goddard. And his research activities over the years have included developing and applying both experimental and remote sensing approaches to research in interdisciplinary earth sciences. And without further ado, Dr. Ichoku, the floor is yours.
All right, thank you very much, Jeanette. Thank you for that great introduction, and thank you for inviting me to this seminar series. It's my pleasure to be here. So for the next hour, I'm going to kind of show an overview of how I think satellite and airborne observations of fires can help to inform fire management. So, of course, California is not new to fire events. You can see the picture right in front of us of fires that were observed from satellite from a Landsat 8 operational land image, or OLI. You can see on the right side here, of course, you know that the Santa Ana winds contribute to the worsening of fire situation in that region. So the outline of this talk is that I'll go over the significance of fires and smoke emissions, and also look at the principles of fire remote sensing from satellite and from aircraft. And we will look at the emissions estimation from satellite fire observations. And then we'll examine the synergy of airborne and satellite fire observations and their applications. And then we'll look at we examine some outlook for future observing systems that can help in fire management. Let's start with the effects of fires and smoke on the environment and climate. So this picture I'm showing here, this image from satellite, MODIS aboard Terra or Aqua, was taken in 2004 in Alaska. This was the Alaskan fire. You can see this very large plume of smoke that extended. The width of the area we're looking at is more than 2,000 kilometers. So I just use this to illustrate that fire, most times, especially wildfires, can be a disturbance to life, property, ecosystem, and water resources. In areas where people live, the emissions from fires, the emissions of particulate matter and pollutants, gaseous pollutants affect the air quality. Fire smoke, the emitted smoke from fire can affect cloud microphysics and heating rates of the atmosphere. And the smoke plume, if it's brighter than the surface over which it's flowing, it can reflect radiation back to space, thereby resulting in cooling of the atmosphere. Whereas over surfaces that are much brighter, it can absorb and result in warming. And when a black carbon in smoke is deposited on snow and ice, it can help accelerate melting. Where do fires occur? It's not only over the US and Canada. You can see globally that this map you're looking at is the fire detection from MODIS in 1 year, the year 2003, with nothing else plotted, just the points where the fires were detected. We see that it creates the map of the world. So fires occur everywhere there is vegetation. And you can see the only places you see spaces are over the ocean, over the drylands and the arid areas, and the areas in the north with the snow and ice. So this is a global annual issue globally, fires, consuming about 3.1 megatons of biomass containing carbon, of which 1/3 is emitted to the atmosphere. And we see that fires contribute about 40% of the black carbon emitted and about 25% of the current day emissions of carbon dioxide. So many of you already know that smoke from fire contains various substances that that affect the air quality and climate. So for instance, here we see that the aerosols, the particulate matter, one of the 6 criteria pollutants of the EPA, so are carbon monoxide, methane, not methane, but NOx and others. And carbon dioxide and methane are forcing constituents in the atmosphere. So some of these substances are, for instance, for the gases emitted from fires from the Actors Field campaign that we conducted in 2008, it was found that carbon dioxide and carbon monoxide and methane together constitute 98.6% of the measured carbon emissions from fires. And carbon dioxide and methane are the 2 most important anthropogenic greenhouse gases in the atmosphere. So in North America, we using satellite observations, we have been able to see the annual cycle of biomass burning in different parts of North America, as you can see on this map, with the colors showing the months with the peak biomass burning. Of course, the annual cycle throughout North America, the peak burning happens in July. But in different parts of North America, the peak burning can happen at different times. For instance, where you are in California, normally it should be in the fall, but sometimes, as you can see the colors there, it can happen as late as late fall, as you can see the greenish colors there. An example is this observation I showed in my first slide from Landsat. On the left side is the true color image that was observed early this month on December 3rd. You can see, and on the right side, you will see that you will see a little bit of the smoke, but also you see the burned area throughout that time period. So if you see at the bottom of the slide, so normally the peak season, the peak fire season in California is between May and October. But because of the rising temperatures globally, now the season is extending to late fall, like December, as you see here. And if you go back a few years ago in 2007, 2017, you will also see a similar event that took place about the same time of year on the 5th. And the left side is from Terra MODIS, and the right side is from the Sentinel, showing the burned area and the flaming front and the smoke plume. A recent study has shown that indeed fire in California, and this is not my study, this was published recently last year by Williams et al., as you see here at the bottom, that it has increased, the burned area in California has increased 5-fold since 1972. So fire, the incidence of fire has been increasing over the years. Indeed, when you look at this table that I downloaded from the CAL FIRE site, you will see that of the 20 largest fires in California, in time, most of it happened in the last few years, particularly in 2020. 2020 saw many of the largest fires, of the top 20 largest fires that have occurred. So let's look at how we observe the principles by which we conduct remote sensing of fires. So based on the Planck's law of radiation, we know that all bodies, all physical bodies of temperature above absolute zero emit some kind of radiation. So, and the peak wavelength of radiation of any body is inversely proportional to the temperature of the body. This B here is a constant. So for fires that lie in the range of from smoldering around 600 Kelvin to about 1200 Kelvin, the peak wavelength of radiation would lie in this range, in the range of 2.4 to about 4.8 microns, with a median around 4 microns. Now, coincidentally, the atmosphere has some gases that absorb radiation, right? So this plot you see here is the transmittance of the atmosphere. And fortunately, that area, that region where fires have their peak radiation is also the most transmissive part of the atmosphere. So that enables observation of fires to happen from space more easily than other features on land. This is an example of an airborne image of a fire that was observed in 2007. So if you see here, you will see the wavelengths of these different bands of the multispectral sensor called the AMS, the Autonomous Modular Sensor. It's an aircraft sensor. And you will see that in the visible region, you see the smoke, but you don't see the heat from the fire. Whereas when you enter the mid to long wave infrared, you see the fire, you don't see the smoke, because the atmosphere, the smoke becomes fairly transparent at that time. And of course, you still see some background signal from the surface background. And in the case of the shortwave infrared, you still see some smoke. Now, in the around the 4 micron region, you will see mostly the heat from the fire without seeing a signal from the surface background or the atmosphere. So that's why the 4 micron region is a very good region for fire remote sensing. An analysis that was conducted by another group, modeling simulations of many different temperature ranges of fire from smoldering to flaming, show that 98% of the variance in fire radiative power, that is the radiant component of the heat released from fire, is explained around the 4 micron wavelength. So This is the graph that illustrates that, which shows that the 4 micron region is the ideal region for fire remote sensing. Okay. So let's talk about emissions, how we estimate emissions from satellite fire observations. Now, the traditional way to estimate emissions of smoke, any constituent of smoke represented by emissions here from biomass burning, is to determine the emission factor. And the emission factor is how much is emitted of that particular constituent relative to the amount of biomass consumed. So it is the emission factor, then you multiply it by that biomass consumed, and you're able to derive the emissions from that fire. That is the equation that relates them. Now, emission factor can be determined in the field or in the laboratory. But then the burn biomass is it's not easy to determine because it's a function of the area burned, the biomass density, the amount of biomass consumed, and the combustion completeness. So all of these factors can contribute to a lot of uncertainty. That is the way that some emissions data sets are currently determined. So from satellite, based on the detection of active fires or burn areas from different satellites, this very well-known data set is using this method to quantify emissions. So, so based on using the detections and the burn area, you're able to estimate the amount of biomass burned, and then multiply it by the emission factor. And then several years ago, many different groups started looking at how to simplify this process and also mitigate the uncertainty that is incurred while trying to quantify emissions this way. So basically, if you look at this fire, this image we're looking at here now at the lower left side, you will see when a fire is going on, two things are very obvious. One is the heat energy released. The second thing is the smoke. And both of these can be measured by remote sensing, can be observed by remote sensing. So for instance, the heat energy release is observed in terms of the fire radiative power. That is the radiant component sensed from space. And we're able to measure this from now various instruments that fly in space, like MODIS on Terra and Aqua, VIREX on SMUMI MPP and the JPSS, and so on and so forth. So a number of groups started working on that. One of the groups used this FRP, this fire radiative power, FRP, integrate over time to get the fire radiative energy, and is able to use that to estimate the burn biomass and then multiply by the emission factor as determined from the traditional way of quantifying emission. And that group was led by Worcester, and that led to this fire emissions data set called GFAS. Now, our group approached it differently, whereby we said, okay, this is measured directly from satellite. We can then actually, rather than rely on the emission factor we just determined in the lab, we use observations of atmospheric constituents from satellite to quantify and emit what we call the emission coefficient. And so we have published a number of articles relating to this methodology. So let's look at the way that the first method approaches this issue. So they set up some vegetation on a scale. You see it down here, and set it on fire, and then put a radiometer here at the top of the tower, and observe that as as the vegetation is being burned. So in the end, you see the fire radiative power as you're observing it. It peaks and then it goes down. And then when it is integrated over time, and the final mass of the residue is subtracted from the original mass of the vegetation, you're able to see the amount of, you're able to determine the amount of biomass consumed, and you're able to relate it to the total fire radiative energy. So by so doing, they are able to generate a plot of this nature, which allows you to get the relationship between the biomass burned and fire radiative energy. And so that is then used to determine the burned biomass. So in our case, since we also measure or retrieve aerosols from satellite, and they also retrieve fire radiative power from satellite, we used wind fields from assimilated data sets to analyze the direction of the plume flow, thereby quantifying the rate of emission of this smoke. And so the fire radiative power is the rate of release of the of radiative energy, whereas we determine also the rate of emission of smoke particles. So we're able to also do the regression least squares fitting by, first of all, remove the outliers, and we're able to fit this zero intercept regression line, whose slope represents the fire radiative power related emission coefficient, which I mentioned here. If we go back to here, which was mentioned here, this CE right here. So that's how we determine that. So based on doing this, analyzing the data, in this case, we used MODIS Terran Alpha data of fire radiative power measurements, as well as aerosol optical depth and the wind parameters. We're able to determine the emission coefficient map globally, which then, whenever we measure, and this is a gridded emission data set, which whenever the fire radiative power is measured from space, we simply multiply and we're able to determine the rate of emission of the aerosols. In this particular case, we call it the total particulate matter emissions from fire. So in this case, for instance, we are able to quantify the total aerosols emitted from fires in 2010. So that's the process of doing this. So the two groups actually work together in the lab to evaluate the approaches that we're using. So we worked together, we went to the Missoula Fire Lab and set up the same type of experiment. There was scale here, some fuel, light it on fire, and put the radiometer here. And then we developed this transmissometer, which enables us to measure eventually retrieve the optical depth of smoke plume. So when this is being burned, as you see here, the red curve is the fire radiative power, whereas the blue curve is the particulate matter emission rate. So we conducted this for a lot of samples of fuel samples, and we're able to develop this kind of plot where we have the fire radiative energy here on the bottom and the total emitted particulate matter. And the slope we got here, which is the emission coefficient, was within the same range of values as what we get from satellites, so which goes to validate the approach that we're using. I forgot to say that at the bottom, I always mention some publications that related to each of the slides here. So we've published these results in case anybody is interested in seeing them. Recently, we compared some of the major emissions data sets, global emissions data sets. We made the comparisons globally as well as regionally in some different, the world, the land surface part of the world was divided into different biomass burning regions. So we made these comparisons as you can see here. And these are the main biomass burning emissions data sets we compared. You will see overall that they differ. So this is the global total of the emissions of organic carbon, for instance. So these different data sets, the global total for this year was this. So there is a very big difference. And in terms of region, biomass burning regions, the differences are large. So here we computed the coefficient of variation of these different emissions data sets and ranked them from 1 to 14. There are 14 different regions. 1 is where the agreement between them was best. 14 was where the agreement between these emissions was the worst. So the agreement between the emissions was best in the Northern Hemisphere African region. Okay, now the agreement was over the tropical North America, that is over the United States. The agreement was not too good. So we also used these different emissions data sets and put them in the NASA GEOS model and compared the simulated aerosol optical depth with the satellite retrieved, MODIS retrieved aerosol optical depth. And here we're looking at the Southern African region and the South American region. These are the two regions where during the biomass burning season, biomass burning aerosols are the dominant aerosols. So with little to no contamination from other types of aerosols. So these are the purest biomass burning aerosols you can get. So we made the comparison of the simulations of aerosol optical depth and the satellite aerosol optical depth. For instance, this is a satellite value from MODIS. This is a simulation where there is no biomass burning. And then these are the simulations for the different biomass burning emissions data sets. We see that these last two, FIR, which is our data set, and QFED, which is another NASA data set, were the ones that were closest to the satellite retrieved aerosol optical depth. Probably because, one of the reasons could be because these two data sets employed in one way or the other the satellite retrieved aerosol optical depth in developing the emissions products, because they use the method that I explained previously, where we calculated the emissions coefficients using different approaches, but then multiplied by fire radiative power from satellite as well. Another aspect to review is the relationship between fire radiative power, as you see here, and plume injection height. So one of the studies we conducted some time ago was just looking at how is it related? How is fire radiative power related to the plume injection height? Of course, the higher the fire radiative power, the more the rate of combustion of biomass. And so depending on the relationship between the fire size and the pixel size, you may have the higher intensity. Anyway, what we're finding is that the fire radiative power is positively correlated with plume injection height and atmospheric stability, as we see here. Okay, excuse me, just need to drink water. Okay, now let's go to how we try to see how we can leverage the synergy between airborne and satellite fire observations in applications. First of all, we'll look at the sources of uncertainty in satellite fire measurements, because even though the satellites have enabled us to really improve the monitoring of fires, there are still some limitations. The limitations can come from, the uncertainty mainly can come from the some intrinsic sensor imperfections. And, there are also spatial resolution limitations, and the fact that satellite observations can omit small fires sometimes. So if we observe at higher resolution, there is a tendency for saturation because the intense signal can saturate the dynamic range of observation of the fire instruments. So sometimes clouds obscure the fires that we are looking at. And then sometimes there is limited diurnal sampling, except of course, observations from geostationary satellite sensors, which have limited spatial resolution. And then there are also imperfections in the algorithm and other things. So an example of one of those issues is the observation geometry issue, something we call bow tie effect from MODIS, which is still there. And I can show you the example in the next slide, where because of the scan angle of movement of, the scan angle difference from nadir to edge of scan, the pixel is not always constant. The pixel size is not constant, it's changing from nadir to far off nadir. An example is this image of the station fire that happened near Pasadena several years ago, about 10 years ago, 2009, I think. If you see Terra MODIS, of course, MODIS is the same instrument on Terra and on Aqua. So at this time, around noontime, it was observed at nadir by Terra. And about an hour and a half later, it was observed by Aqua. Same MODIS on Aqua, but now no longer at nadir, but off nadir, well off nadir, same fire. Within this short time interval, the fire would not have changed very much, but there is a big difference in what we are seeing here. So you will see that the total fire radiative power was 28,000 megawatts because it was observed here near nadir, whereas when observed at the very edge of scan, it's about I would say 1/6 of what was observed near nadir. So this is something, a challenge that we also need to figure out how to deal with. So we've been looking for a way to understand how to deal with such uncertainty that arise from measuring, observing fires, measuring fire radiative power from space. And so we have been involved in a number of field sampling, field campaigns that involve the use of drones. If you look at this image here, you will see this drone here. We conducted this in the Kansas prairies, where we had drones with some small instruments that that sample the smoke, whereas the instrument that is carrying the sensor, the remote sensing instrument that's looking down, is on the drone that's higher than this, what we're looking at now. So we're trying to understand the relationship between this fire radiative power and the smoke emission rates. So at every scale, we've done it in the lab. Here we are doing it. So anyway, while we're doing this, an opportunity came last year with NASA and NOAA collaborating to organize this very large field campaign in 2019 called FIREX-AQ. I think that many people who are watching this may have participated because it's a very, very big campaign which involved 2 major aircraft from NASA, 2 smaller aircraft from NOAA, and many other groups from the community and from other organizations. So in 2019 summer, we were first stationed in in Idaho and then in in Kansas to look at the different types of fires, the wildfires in the west and the controlled fires in the southeast at different times. So there were different teams based on these different aircrafts, and we were part of the NASA DC-8. You can see this image we took of the participants in the beginning of the deployment in Boise, Idaho. So there are a lot of instruments. So one of the things I have to mention is that the fire remote sensing instrument that we used is called MASTER. MASTER, that's a MODIS and ASTER airborne simulator, which was located here. And as we flew along, it observed the fires while the other instruments, you can see many of the probes coming out of the aircraft window and other parts of it. So very many different observations were collected during that field campaign, which we're still in the process of analyzing. So, well, you see the way that the flight tracks are going over the fire and then following the plume and so on and so forth. So this is an example of different bands from that master airborne sensor. So this one is the actual, the one we regard as the fire channel, as I showed in the beginning from a different aircraft, a different airborne instrument. So you see here the fire, in the other ones you see the smoke. This image I took myself from the NASA DC-8 aircraft. So what have we done with the data? So what we've done is to develop an algorithm to, first of all, calculate the fire radiative power at, you see here, very high spatial resolution of the master. So from the aircraft, we can observe fires. I forgot to mention that from MODIS, the spatial resolution of fire detection at nadir is 1 kilometer, whereas from the aircraft at the altitude we were flying using the master instrument, the spatial resolution was of the order of 20 meters, which is very high spatial resolution. So here we show the fire radiative power. On this side, we are experimenting on trying to segment the pixels we see in terms of smoldering, flaming, and sometimes because of the closeness of the instrument to the fire, there's some of the observations are saturated. So we show some areas that are saturated. But the advantage we had of using the aircraft airborne observations of the fire is that it now allows us to see the fire shape, and we are able to calculate the area of the fire, the active fire at the time, and we can, to some approximate extent, you know, the way we have shown here, determine the flaming, smoldering regions of the fire. But also, as I've indicated here, that we have the problem of saturation because the instrument saturates at about 640 Kelvin, whereas vegetation fires can sometimes even reach 1500 Kelvin. So we have this problem of saturation with the instruments we currently have. We currently have everywhere, you know. So one thing we've tried to do is to try to compare the observation from aircraft with observation from satellite. So in the case we're looking at here now, the left image is the image from master showing the fire, and you can see the fire front, the flaming part of the fire, of this particular fire, Williams Flats fires, that we observed on the 3rd, and on the 3rd of August of 2019. Now, the corresponding fire detection from the VIIRS instrument on the SUMI NPP shows that the fire outline agree. So there's good agreement between the aircraft and the satellite observations. The VIIRS fire detection pixels were observed at 750 meters. whereas this one is observed at 20-meter resolution. But even then, there is good agreement between them. So we have compared these two data sets, the aircraft and the satellite for the entire experiment, the entire field campaign. So you will see on the left side, these are the Western US fires, and these are the Southeastern US fires. In most cases, they generally agree, but of course, there are differences. You'll notice, given that this scale is a log scale, you will see that the Western fires are at least one order of magnitude larger than the Southeastern fires. That's, of course, well known. But one other thing to observe is that the aircraft instrument underestimates most times relative to the satellite instrument. Why? Probably because of the saturation. So because of the saturation of the observing of the pixels, the FRP is underestimated. So that's one of the reasons we think is why they are generally the aircraft measurements generally underestimate. One of the things that the aircraft measurements can help us do, excuse me, is that we see the same Williams-class fires observed at 3 different times from aircraft. So probably about 2 hours apart each. So we'll see, this is on the left side is the fire radiative power, and on the right side is the segmentation in as flaming, smoldering, and saturated. So if you see this circle, you will see the progression of the fire as we see here. So we went and observed and came back and observed and came back again. So several times. So in this area where you see based on the fire radiative power, it's hottest, that's where the fire is actively progressing. So we see by the time you get back, you will see that it's moving forward and covering that region. And then finally, they are touching. So the region where it is most actively burning, where the power is highest, that is where the progression. So by having this capability to look at the fire radiative power at high resolution, we're able to determine or even predict where the fire is going to be advancing as we move forward. So that's one of the advantages. Another method which is related to that is that one of our of the other groups we collaborate with is using a different approach where the satellite veers, the veers instrument on the satellite also has what it calls the broadband day-night band, which sees visible light. So from the visible light, you can quantify the visible energy from the visible light. And this is in the visible region of the spectrum, not the infrared. And then from the infrared, the mid-infrared, as we do, we measure, we calculate the fire radiative power. So the ratio between them gives you the visible energy fraction. So the visible energy fraction can allow one to predict where the fire is going to advance. So this was observed, if you can see the date here, on the 7th of August at about 10 o'clock UTC. So about 8 hours later, you will see that the area where it is predicted that the fire will advance, this was observed during the daytime. These observations were collected during the nighttime, and 8 hours later, we see that the fire is actually advancing in the region where it was expected to advance. Another aspect that we are looking at is that we able to simulate using WRF-Chem, which is a mesoscale model, simulate the plume, the smoke emission from the fire, and we're able to verify using the measurements we collected during the FIREX-AQ. Okay, so we're still in the process of doing all of these verifications as we speak. Okay, so what about what do we do in the future? Since we know that what we currently have is not optimal. We've been looking at this question for a while. For instance, we know that it's good to improve the observation, the resolution of observation, and also to improve the dynamic range. Because what problem are we showing, for instance? This image in the background here is an aircraft image showing, and we use the same method to segment into flaming, smoldering, and saturated in this image. But now we superimpose the footprint to scale of the different satellite sensors that we have in space that can measure fires, that can observe fires and calculate fire radiative power. So you will see GEOS, this largest footprint of GEOS. Then, oh no, sorry. Yeah, it is the GEOS imager, this large one. And we see the MODIS. MODIS is the green one. So at nadir, this is the footprint at nadir. Whereas at the edge of scan, you have this green one, the larger green footprint. Now, the higher resolution GEOS, the GEOS ABI, that is GEOS 16, is this one here. Whereas VAERS at nadir is a higher resolution, like 750 meters, whereas at the edge of scan is 1.5 kilometers. So we are suggesting that for space observations of fires to really be very useful in fire management, we need to have very high resolution from space, like 50-meter resolution from space, in order to get the detail that's needed. And also not only the spatial resolution, but also to have the dynamic range to avoid saturation, in order to improve the way we use satellite observations to manage fires. So if we get the higher resolution in 50 meters, as we are suggesting here, and the full dynamic range, we can quantify the temperature and emissivity of the fire, and which are relevant for many of the calculations we make. And we can calculate the fire radiative power and estimate the active fire areas, the flaming, smoldering, and also the smoke emission and plume injection. So last year, we proposed an instrument that can do this, that we ultimately, first of all, we developed the instrument, then we fly on aircraft to test it, and then we fly it on CubeSats. Well, our proposal was not selected. So these were the specifications we proposed. And so from aircraft, we can conduct test flights, and finally, we can fly in space. So the recommendation we made for flying in space, if it were selected, which it was not, but of course, there are still opportunities to repropose this in the future, is to set it up in such a way that we will have several. First of all, we can look at the visible part, the shortwave infrared part, and the infrared part, where we can actually do the calculations of fire radiative power and emissivity and others. So this is the configuration we were recommending, but we're still looking forward to getting the opportunity to make this happen. And I know that a number of other groups are looking at this same question to first improve the spatial resolution from space, using maybe a constellation of CubeSats, and also to improve the dynamic range in order to avoid saturation, which can be used to, alert, predict fire propagation and emissions. So in summary, we say that wildfires and other types of biomass burning affect the environment in ways that have adverse impacts on wide-ranging societal concern, from health to climate. They have increased significantly in North America over the years because of the rise in temperatures, particularly in California. And efforts are being made to improve the way that we understand and observe fires. But we still need more work. We still need to do more work in improving the observing systems in order to better handle the management of wildfire drivers, their energetics, their emissions, and their impacts. I have listed a few of the references I cited in this presentation, and I acknowledge some of the support I've received from NOAA and from NASA, and some of the teams that have contributed to the presentation I've shown. And over the years, while studying fires and emissions, I have had to collaborate with a large number of people. I cannot mention all of their names, but the names of a few of them are here. That's it. Thank you very much.
Thank you, Dr. Ichoku, for such an interesting presentation. We do have quite a bit of questions. We'll try to get through as many as we can during this session, and those that we don't have time to answer, we'll move them over for the discussion section. So the first question is asking they're asking how they estimate beta, the combustion completeness.
The combustion completeness, it's hard to tell, but different people estimate that in different ways. Sometimes they use something they call I forgot the name of that parameter that they estimate, and they're able to. So the combustion completeness is how much of it is burned and out of the total fuel that you have in the field. So they have different ways of estimating from satellite observations. I don't remember how to describe them, but there are various people do it in different ways, basically. If you were doing it in the lab, it's easier, then you can do it, but from satellite, there are various algorithms that are applied, which I'm not very, very familiar with.
Thank you. We have another question, and they're asking, how can satellite and airborne observations help us improve smoke-related public safety alerts that typically only include AQI numbers? Are there patterns here that should be communicated to the public to help them avoiding negative health consequences of wildfire smoke exposure? And they also ask, are there different combinations of smoke-related data points? And they point out examples, biomass density, combustion completeness, etc., during wildfires that should trigger different types of smoke alerts for the public and first responders.
Yes, the ways that the satellite observations of fires can help us to predict the potential impacts of smoke is by generating the emissions in near real time and including them in models, in air quality models. We can then predict where they will go in the following days. So that's basically the most feasible way to actually predict where the smoke will go and where it will impact. People have used different kinds of models. People have used, things like trajectory analysis. But one of the methods we have developed here is to actually derive the smoke emission rates in real time. Actually, that was what drove our approach at determining the globally gridded emission coefficients, so that in real time, in near real time, not in real time, near real time, once you observe the fire radiative power, you simply multiply, get the emission rates, put it in the model, in the air quality model or other mesoscale models, and then see how the smoke is dispersed. And then you'll be able to show the areas where the smoke will impact.
Great, thank you. And speaking of emission coefficients, there's a question that's asking how consistent is the emission coefficient for a particular region? Is the coefficient impacted by factors such as weather during the season leading up to a fire and fire history in the preceding years?
Yes, the emission coefficients we have determined, we did not, basically we used data observed over a period of 8 years to determine that, because we had to have enough statistical representation of data to calculate the emission coefficients. So we did not try to consider other factors. Of course, the other factors play a role. The weather, the weather and the type of biomass, the fire regime, and other factors play a role. But this first version we have developed, we did not consider some of those subtle nuances. We simply used the emissions, the aerosol retrievals and fires from the MODIS sensor over the period of 8 years and determined that. So in future, all of those factors will be considered, including the diurnal cycle, the changes in the emissions depending on time of day, and even depending on how moist, the moisture, the humidity in the vegetation, how moist the vegetation is, and the humidity in the atmosphere. All of those things can affect the emission rates, but they were not considered in the first version of the product that we currently have.
Thank you. And we have time for one question, so I'll read it out, and whatever we have left, we'll move over to the discussion session in which we have the link currently in the chat. But this last question asks, do sensors for laboratory, airborne, and stratospheric and spaceborne measurements vary in the spectral bands used? And they also ask, what are the key aspects one should take into consideration for combining data from different sources? It's a great question.
I missed the first part of the question. Can you ask it again?
Yeah. Yes, they ask, do sensors for laboratory, airborne, stratospheric, and spaceborne measurements vary in the spectral bands used? That's the first question.
Okay, so you were asking whether the sensors vary.
Yes, they're asking whether the sensors vary.
Yes, the kind of instruments you use to measure, depending on what feature or what atmospheric state you want to sense, the spectral band that you place in the sensor will vary for sure. That's why you have different kinds of spaceborne sensors up there. Some of them focusing on, like the OCO, focusing on the carbon dioxide. Some of them focusing on other types of gases. Some doing mostly aerosols, and others, some doing surface. And then there are other variations, not only the spectral differences, but also the spatial resolution differences between them. And even the angular differences between the way that they observe. For instance, let's say, for instance, MODIS observes is nadir observing, whereas MISA is observing at different angles. MISA is, both of them are on the Terra satellite. So yes, there are, whatever, depending on what you want to observe, you have to design the instrument to, to enhance the instrument's capability to observe what you want to quantify.
Thank you. Those are great points. We're all out of time for the seminar session. Please join me in virtually thanking Dr. Ichoku for his time and giving this very interesting talk for us. And for those of you who can join us, please check out the link in the chat, and we'll navigate over to the separate Zoom session to continue the conversation. Thank you. Thank you, Dr. Ichoku.
Thank you. Thank you.